Welcome to particles, antiparticles and protons. So we've looked so far at the subatomic particles, the proton, the neutron and the electron. All of these have their own antiparticles. There is the antiproton, there is the antineutron and there is the positron. And wherever possible, the properties of the antiparticles are opposite to the properties of the normal particles. So for example, the proton has a positive charge, the antiproton has a negative charge. The neutron has no charge, and it's not possible to get the opposite of that, so the antineutron also has a zero charge. The electron has a negative charge, and the positron has a positive charge. Their masses are the same, so the proton and the antiproton, the neutron and the antineutron, they've got the same masses as their regular particle. So for example, the electron has a mass of 9.11 times 10 to the minus 31 kilograms, and so does the positron. They both have the same mass. You can't go the other way. You can't have an opposite mass. So it's just the same. So they are the equivalent, but opposite where possible. Every particle has an antiparticle. Some of these particles are not fundamental. The proton and the neutron can be broken down into smaller items. The electron cannot. And all of those smaller particles each have their own antiparticle. So here we have a table of the different types of fundamental particles. You can see on here that the electron is an example of a lepton, and the particles that make up protons and neutrons, those are quarks. And every single one of those quarks has an antiparticle, an antiquark. And I will show you what those are. The regular quarks are up, charm, top, down, strange and bottom. The antiparticles are anti-up, anti-charm, anti-top, anti-down, anti-strange and anti-bottom. And we would usually write these using their first letters. So we have the up, the charm, the top, the down, the strange and the bottom, the anti-up, the anti-charm, the anti-top, the anti-down, the anti-strange and the anti-bottom. And the leptons also have their own antiparticles. When we are talking about some of the properties, some of these might be a little strange to you. So for example, charge. Quarks have a fractional charge. The up has a charge of 2/3, and the anti-up has a charge of negative 2/3. The strange quark has a charge of minus 1/3, and the anti-strange is a positive 1/3. So it's the opposite, but it's the same magnitude. The masses work in the same way that they did with the electrons. They have the same masses. We also have something called rest energy. And rest energy is the amount of energy that that mass has. Rest energy. If we have a look at the rest energy of the electron, we can see that it's the same as the rest energy of the positron. And that is, so the rest energy of an electron is equal to 0.511 mega electron volts. And an electron volt is a type of energy. So this is 0.511 times 10 to the power of 6 multiples of 1 electron volt. So the way that you would transfer that into joules would be to say 0.511 mega, so times 10 to the 6, and then multiply that by 1 electron volt. So 1.6 times 10 to the minus 19 joules. And that will give you the energy in joules. Okay, let's have a look at photons. You can see from the model that the photon is included and it is a force carrier. We're going to be talking about some of these later on in the course. We're not going to be talking about the gluon, the Higgs boson, or the Z boson. We are going to be talking about photons and W bosons later in the course. We're going to have a quick look at photons now. So we know about photons being a particle of light, and you should be familiar with the electromagnetic spectrum, sometimes shortened to the EM spectrum, the electromagnetic spectrum. And this diagram here shows the electromagnetic spectrum. It shows the wavelength and the frequency, and you can see that those have an inverse relationship. So the frequency is increasing in this direction, and the wavelength is increasing in this direction. So if we have a continuous wave, then the wavelength is the distance between repeating parts of the wave. You can measure it peak to peak. You could measure it trough to trough if you prefer. Personally, I prefer to go this way. Any of those are going to be correct. The relationship between wavelength and frequency is this equation here, where this is the velocity of the light. And the velocity of light is 3 × 10⁸ meters per second. So you should be familiar with those concepts. Now, at A level, we learn that light doesn't exist as a continuous wave. It exists in particles. And you can imagine a particle of light as being a very short portion of the wave. It has a frequency, it has a wavelength. And there are equations for you to calculate the energy of that particle of light, that photon. Okay, so what we're doing here is we are using the relationship between frequency and wavelength, and we are substituting this equation in order to turn this equation into this one. Okay, so we can substitute that information in. This h is a constant, and it's called the Planck constant, and it has a value of 6.63 × 10⁻34 joule seconds. Okay, and what that does is it allows us to calculate the energy of one particle, one photon of light. Let's have a look at some examples where we can use this information for some useful calculations. Okay, so in a hospital, you might be given something called a PET scan, positron emission tomography. Tomography being a word related to mapping. Positrons are the antiparticle of the electron. Positron emission, or giving out, mapping. So what we're doing is we're making an image of the human body using positrons that have been given out, and we are collecting them and making an image out of them. So the way that it works is that the patient is injected, and you'll notice that the syringe here is rather unusual. The patient is injected with something called a radionuclide. And that is a radioactive material that gives out positrons. It goes into the body and is absorbed by the body in whatever way this medicine is designed to be absorbed. Maybe they're taking an image of the patient's bones or other different types of tissues, and they have treated the chemicals so that the human body will absorb it in a particular way. A common way of doing it is to mix it with sugars so that you can see which parts of the body have a higher metabolism, which parts of the body are growing and repairing at a higher rate compared with the others. And that's particularly good at identifying things like tumours, cancerous tumours, because cancerous tumours are going to be absorbing sugar and growing more rapidly than other parts of the body. So the way that it works is that positrons are emitted by this radioactive material, and when they collide with an electron, they produce a photon of light, and it's a gamma particle. If we have a look back at the previous diagram, we can see that the gamma rays are at this end of the electromagnetic spectrum. They're quite high energy, high frequency. Notice that high energy would correlate with high frequency. The higher the frequency, the more energy. That gamma photon is identified by the scanner, by the PET scanner, and then an image can be put together from all of these gamma rays that are given out. Notice here is an example of an X-ray, and here is an example of a PET scan. This is much more detailed, and it shows the function of the human body rather than just the hard structures within the human body. So this is showing the uptake of sugars by the body, and you can see that the brain is very, very active, because the brain is a very, in terms of energy, it's a very high demand organ. Okay, so we're going to talk a little bit about some of the functions behind the way that this works, and you need to know about two things. You need to know about annihilation. And you need to know about pair production. So annihilation is the way that the PET scans work. And what happens is that you have a particle and its antiparticle coming together, and when they are in the same place at the same time, they cancel each other out. They annihilate each other. And what happens is that their masses are turned into pure energy, and that is in the form of a photon. Pair production is the opposite of this. So this is how a PET scan works. The photon is absorbed and used to create the image. The opposite of that is pair production. And that's where you have a photon, pure energy, generating a particle and its antiparticle out of nothing. So you get pure energy and it becomes mass. You can calculate the frequency and the wavelength of the photon involved in either annihilation or pair production by analysing the rest energies of these particles. So what you would do is you would add together the rest energies of the particles involved. So you would add those together, and that would give you the energy of the photon that would be produced. And then you can do the reverse with pair production, where you have a photon with E equals HF, and that is going to turn into the rest energies of the particle and the antiparticle that it's going to generate.